This video is going to cover how to draw Mohr's circle. Mohr's circle is a wonderful visual representation of the state of stress. So effectively we're doing all those transformation equations, but this time visually, which I personally prefer to do. So we're just going to kick it off with an example because honestly, there's no new equations to talk about. So we have a state of stress, and in this state of stress, we're going to have a positive sigma x. We're going to say maybe 15 psi. We're going to have a negative sigma y. Let's say that's going to be 20 psi. And then we're also going to have a shear stress, and that shear stress is going to be positive 10 psi. So again, I'm saying positives and negatives, but of course it's always really nice because you're probably just going to be given a picture to write out what they are. So again, we had sigma x, and we did say that it was positive because it's in tension, it's going away. So sigma x is a positive 15 psi. We said that sigma y, because it's going into the face, that's compression, so that's going to be minus 20 psi. And we said that our tau xy, our shear stress, is a positive 10. Now it's positive because it's going up to that top right corner. So this is positive 10 psi. So again, we did actually have a whole bunch of lovely transformation equations, which are kind of disgusting. And they're great if you want to know the state of stress at one particular point. However, we had a lot of other equations that we could have used to find things like principal stresses. So just to remind you what our principal stress equation was, we had sigma 1 and sigma 2. And that equation was sigma x plus sigma y divided by 2 plus or minus, depending on whether you're 1 or 2, the square root of sigma x minus sigma y divided by 2 squared plus tau xy squared. So this equation actually really helps dictate out everything that's about to go on with the circle. To draw a circle, you need to know a few pieces of information, namely the center and the radius. From there, you can draw a circle. So, fun fact about the center, this is the center. We also called this sigma average. So this is the equation for the center of the circle, which was sigma average. And the radius of the circle, let's do a different color, is this guy, which again, we called tau max, right? Tau max in plane, technically. So effectively, the equation for Mohr's circle is already given to you in terms of the principal stresses. And this makes sense because the principal stresses lie on our x-axis here, our horizontal directional axis, in the most positive and the most negative. So again, it's really obvious that if you go from the center and you add the radius, you're going to get the most positive. And if you go from the center and you subtract the radius, you're going to get the most negative. Hence, again, our two principal stresses. So again, we need to calculate the center. So step number 1, find the center. And our center was sigma average, which is sigma x. Our sigma x is a positive 15, plus sigma y, ours is negative 20, divided by 2. And what we're going to get is negative 2.5 psi. Okay, we're going to go plot that on a graph. Then we need to calculate the radius. And the radius we just said was tau max. And our equation was the square root of sigma x, which is 15, minus sigma y, who is negative 20, divided by 2 squared, plus tau xy, which was a positive 10, squared. So what we're going to get on this dude is 20.2 psi. So again, we're just going to, step number 3, draw the circle. So a couple things before we can draw the circle is talking about our axes here. So I'm going to zoom out quite a bit here to get a nice sized circle. We have vertical and we have horizontal axes for our circle. So obviously, like I just said, sigma is on the horizontal axis. Positive sigma and our positive x direction makes good sense, right? So going over to the right is positive, and whereas going over to the left is negative. For normal stresses, normal directions kind of make sense. But for shear stresses, if you haven't already seen a trend with everything to do with shear, it's backwards. So obviously shear is going to be our vertical axis here. However, if normally we would consider up to be positive, but this is shear, and shear is backwards, then down is positive. And yep, there it is. So down is positive for our shear axis. So now that we have our axes, now we need to draw a circle. So we need to first start by locating the center at that negative 2.5. I didn't know, maybe about right there. There is our sigma average, who is negative 2.5 psi. Should probably not have written him all over the place. We'll say negative 2.5 psi up here. Okay, cool. Then I need to go out the radius in every direction. So I'm going to add 20.2, and I'll be over here. I don't know, maybe it'll help if I actually like use my straight edge here. Let's just pretend 1, 2, 3, 4. We're maybe about over there-ish. Let's say we're about there. So this is going to be sigma 1. When you do the center plus the radius, you'll be at sigma 1, and that is 17.7 psi in this case. And then we're going to go the other way. 1, 2, 3, 4 will be about here. And this, when you take the center and you minus the radius, you get sigma 2. So sigma 2 is going to be, they're both negative, so now it's negative 22.7 psi. Don't forget, we also got to go vertical, right? So uppy and downies from the center here. So we go up 1, 2, 3, 4, about up there, and then down 1, 2, 3, 4, about down there. So top and bottom, technically, these are both tau max. Obviously max positive, max negative, but they're both tau max, and they're both, of course, 20.2 psi, because that's the radius. Then we have to draw the circle. So now comes the part where you have to not suck at drawing a circle. Technically, there's an 8-point method. If you want to know how to actually draw a circle, I'll just kind of show you really quick. Technically, you're drawing a box. So like in each one of these little quadrants here, we could just draw a box. And then you have a diagonal that goes through it. On each one of these diagonals going from the center of the circle away, you need to go find 50%. So 50% is about right here. And then you need to go another 50% of the farther leg, so about right here. And that, if you go through that point, that will get you a decent looking circle anyway. But if you do that 4 times, 4 different quadrants here, you'll have a decent looking circle. But anyway, we're just going to kind of wing it because it's really not that important. So yay, circle here. I'm kind of decent at circles in some quadrants, not so much other quadrants. But, you know, for a half-assed attempt, I'd say that's pretty dang good. So there we go, circle. I think it actually looked better when I didn't use my method. But anyway, there we go. Nice and beautiful. Nice and beautiful. That's the bottom of the circles right there. It can get a little bit difficult when you have your axes kind of really close to that line. But anyway, ta-da, circle. Next thing that we need to do, actually we're going to come over here, step number 4, we need to plot 2 points. And those 2 points should, of course, lie on our circle unless we messed up. And our 2 points that we need to plot are going to be sigma x and tau xy, and sigma y and negative tau xy. Yes, we need to plot those 2 points. So real quick, what are those numbers? We're going to be plotting sigma x, 15, and tau xy, 10. So 15, comma 10. So I need to go, we'll do it in red, I guess. I need to go out to 10, comma 15. So 10 is, I'll just try and measure here, trying to use our same thing, 5, 10. 10 was about here-ish, and 15 would be about down 3 of these, 1, 2, 3. Okay, well, I didn't actually hit my circle. Okay, tragic. So we're going to say it is about over here because I can't draw. So we're going to say this spot here is sigma x, comma tau xy, which is, of course, did I do it backward? It's 15, comma 10. Well, that would be why I didn't actually hit the circle. Hysterical. Okay, let's try that one more time. We need to go to 15, comma 10. So 15 would be at 1, 2, 3 of these would be out over here, comma 10 would be 1, 2 of these, so about here. Okay, so a little bit closer to my circle. Again, it would work if you had an actual correct drawn circle. So again, sigma x, comma tau xy was supposed to be 15, comma 10. Ta-da. And then if you go to sigma y, comma negative tau xy, that would be negative 20, comma negative 10 for that guy right there. Then negative 20, comma negative 10, we're going to be at the, get this, opposite side if you draw a line through the circle. Yep, so if I draw a line through the circle from the center out to that point, and I go the opposite direction, that is going to hit at sigma y negative tau xy. So kind of cool, right, that those 2 points exist at the opposite ends of the circle, which again, this point was negative 20, comma negative 10. So kind of nifty. So if you were to try and find a state of stress, you would have to look at the 2 opposite corners of your lovely circle. Ta-da. Corners. There's not really corners in a circle. But now that we've plotted these points, usually the next thing that we want to find is what are the orientations of the maximum stresses. Notice that you already found them, right? You already have sigma 1, you already have sigma 2, you already have tau max. So what are their orientations? Their orientations very specifically are measured off of sigma x tau xy. So off of this point, now this point is not always in this bottom right quadrant. They could be backwards, it could be in any one of the 4 quadrants, but you very specifically need to make sure that you're going to sigma x and tau xy. You can't be going to any other line, you have to go to this line. And if you draw the angle off of this line to your horizontal axis when you're going toward sigma 1, that distance is 2 theta p1. If you're going from this line and you're going away all the way over to sigma 2, then this is 2 theta p2. Okay, so kind of simple, yeah, kind of simple. Now, how do you find these things? Well, what we're going to do is triangle math. So it's actually not that bad. So let me draw you a triangle. Here's a triangle. I'm going to cut right through my text there. And here's the other direction right there. So you see, we're finding the angle inside that triangle. There's a little bit of information that we know about this, right? We need to know what this y distance is right here. And we need to know what this x distance is. But because you have these coordinates, this actually makes it pretty easy. So the y distance is simply tau xy, which is 10. Our x distance is technically, we're over 15 from this axial coordinate here, plus the minus 2.5 for sigma average. So x here is 15 plus the 2.5, which is 17.5. So Now, if we want to find 2 theta p1, what are we going to do? Well, we're going to take the arctangent of the opposite, which was y, over the adjacent, which is x. So again, that's 10 over 17.5. Ta-da! And we're going to get that 2 theta p1 is equal to 29.7 degrees. That's 2 theta p1. I think I might have said 2 theta p2. It's 2 theta p1. So 2 theta p1 is 29.7 degrees. Is it positive or negative? Notice I didn't actually care about sign over there when I was doing my triangle, because I'm going to ask myself right now, is it positive or negative? Remember that we always take positive theta to be measuring off the positive axis counterclockwise. Are we going in the counterclockwise direction? Literally come over here and look. Is this going counterclockwise? Yes, it is. So therefore, that is a positive 29.7 degrees. So if I want to know what theta p1 is, it's simply 29.7 degrees divided by 2, which is, lo and behold, 14.9 degrees. Again, still positive because we're still going counterclockwise. Now, if I want to find 2 theta p2, 2 theta p2, if you're just looking at this beautiful circle over here, flat line is 180 degrees, and I know this much of it. So if I want to find 2 theta p2, all I have to do is actually subtract it from 2 theta p1 from 180 degrees. So 2 theta p2 is 180 minus 2 theta p1. So 180 minus 29.7, and we're going to get that 2 theta p2 is 150.3 degrees. However, directions matter. Is it positive or negative? Well, he's going clockwise. So clockwise for us is going to be negative. There we go. Again, nobody really wants 2 thetas. We want simple singular thetas. So theta p2 is obviously negative 150.3 degrees divided by 2. And that's going to give us negative 75.2 degrees. Cool. So Mohr's circle, you can see, is actually really simple when it comes to finding these things. Now there's one more piece of information we want to find. What about 2 theta s? 2 theta s is for our new color in here. I don't know, I guess we're going to draw it in this green color. If you go down from the center, you hit tau max, correct? 2 theta s is the orientation from, again, sigma x comma tau xy to that vertical line. Now again, the maximum could be max negative, it could be max positive. We're going to the closest one. So our closest one is right here. So this is 2 theta s. How are you going to solve for that? Well, it makes a right angle with 2 theta p1, so if I actually want to find 2 theta s, I'm going to take 90 degrees and I'm going to subtract off, again, 2 theta p1. Magical. So 2 theta p1 is supposed to be in the pink color. Trying to keep consistent with this, 2 theta p1. So if I take 90 and I minus off something that's almost 30, lo and behold, for 2 theta s, I'm going to get 60.3 degrees. But again, is it positive or negative? Because he is going clockwise, he's going to be negative. And again, nobody really cares about 2 theta s. We really only care about theta s. So theta s is negative 60.3 degrees divided by 2. And then we're at negative 30.2 degrees. Cool, ta-da. So now we found all of our principal stresses, their orientations, our max shear stress, its orientation, and sigma average, all easily through Mohr's circle. So again, is it difficult? No, not really. The center and the radius are the 2 halves of our principal stress equation, which is really easy to remember. So again, drawing a circle, not too hard, plotting it, not too hard. But get this, we're not necessarily done. We did say this is a visual representation of all of the states of stress. So what if now you actually want to say on your stress element, you want to change this thing and now say that this is at 30 degrees, this plane AB. And now you want to find what are the transformed states of stress. How do you do that? Well, again, a little bit of knowledge about how to do this is that obviously this was sigma x. So sigma x prime is, again, it's a normal force. It's going to be coming perpendicular to that line. That's sigma x prime. So step number one, I need to find what that angle is. How much have I actually rotated it? How much have I actually rotated it? And obviously this is really, really terrible to scale thing. But you do some wonderful geometry here, and you discover that that is actually 60 degrees. So if my actual rotation here, if my actual theta is 60 degrees, and it is going counterclockwise, right, so it is 60 degrees, it is counterclockwise. This is my theta. But again, when you're looking at your Mohr circle, notice we don't plot theta, we plot 2 theta. So if you want to figure out where this point is and just simply read the coordinates off of the circle for sigma x and tau xy and sigma y and tau xy, you need to, again, remember that we are going to find sigma x prime is at this angle here. That angle, 60 degrees. We plot, though, 2 theta. So, okay, that's going to be 2 times 60. That's 120 degrees. Again, still counterclockwise. So from my line, from my current state of stress, this is my current state of stress, I'm going to go 120 degrees counterclockwise. Again, 180 is over here. So I'm going to go a little bit short of that. I'm actually going to ride up to right about here-ish. Yeah, I picked some really bad numbers for this, and it's going to be about right there. So what I need to do now, again, knowing that, oh gosh, new color here, knowing that this is actually my 2 theta, for my new transformed state of stress location. I've gone 120 degrees. I know where that is. I can plot it. And then I'm going to use, look, there's a baby triangle right here. Using some trig, I'm going to calculate what those values are. And again, this point is going to be sigma x prime, tau x prime, y prime. If you want to know what sigma y prime is, then continue on to the other side of the circle, right? And you will find what sigma y prime is. So ta-da. So if you want to actually use Mohr's circle to find the transformed state of stress, you might be thinking, I don't actually enjoy these equations. I don't actually enjoy doing this triangle math and all that other garbage. But you can see visually all of the different states of stress. So yeah, there you go. And by doing so, what you'll notice on this circle is that if you were actually at tau max, down here, what is your value, your coordinate is sigma average, which is why on the state of stress, when you're at maximum in-plane shear stress, both your sigma x and your sigma y are sigma average. So hopefully by seeing Mohr's circle and all of the gloriousness that is this cute little circle and all of his magical states of stress, it makes visualizing what's actually going on with those lovely equations much simpler. I'm not saying that the math is necessarily any simpler, any harder. It's just dependent on whether you like plug and chug or whether you actually like seeing triangles and actually understanding what the angles mean and what the lengths are. But overall, it's not really too terrible of a concept if you get down how to draw the circle.